Worth recording. So we're getting started a little bit late. I apologize in that. So questions about the spec quizzes, just to make sure everybody's kind of aware, kind of behind them. There are a total of, I think, 30, maybe 31 for the entire semester. Right? For exam 1, there are 20 to 21. I'm trusting somebody else's numbers on that. Okay? The remaining quizzes get shuttled into Unit 2. Okay? All of those spec quizzes at another institution were considered Unit 1 material. Right? And I kind of agree with it, except that what I've noticed through kind of history of teaching this class is that there's so much crammed into the first unit that theoretically should have been addressed at previous classes, but wasn't addressed to enough detail to allow us to be functional within it, that we spend a little bit more time going through that content, which then means some content gets shifted into the Unit 2. Okay? And so what I went through and did was looked at the stuff from Unit 1 and said, this stuff I can make an argument for being in Unit 2, and so I moved that across. That then means those spec quizzes also got moved into that Unit 2 section. Unit 2, full disclosure, is crammed with tons of information also. Okay? I don't think it's as dense as Unit 1 as far as bouncing around with also kind of what appeared to be disparate thoughts. Unit 1 is mostly just structure and how do we manipulate that structure all the way through. Okay? Everything you're doing is just looking at structure and the things that affect that. We move into Unit 2, it's now how do we experimentally prove that structure. So there are some specs quizzes in Unit 2 that are still kind of structural based, but they're lab-ish based. The rest of the content within Unit 2 is almost exclusively lab-based. Okay? As content, full disclosure for Unit 2, the majority of you won't need it. And I would argue that content should be moved to the very end of the semester, because at the end of the semester, it doesn't matter what I say. So if you're all like, oh yeah, I'm not listening to you now anyway, Mike, the end of the semester, it's like you shouldn't have even come to class. Like you're just stone-faced, nothing's going through. Okay? And that's a problem because the end of the semester content is relevant for second semester. Whereas our Unit 2 content continues to show up throughout everything, but it shows up in such a small percentage that it's not that big of a deal if you stonewalled it at the end of the semester. Does that make sense? I have to do a whole lot of content shifting around to be able to pull that off, and I haven't done that yet, so we're stuck with Unit 2, stuck where it is. Okay? So it's a lot of stuff kind of crammed at you that you're going to try and practice and get frustrated with. And I know. But then we'll just kind of let it go, and we'll move into Units 3 and 4 that are now going to take all that structural stuff and say, how can I make reactions? How can I make stuff? Now that I know what I'm looking at, how do I make it look like something else? That, I think, is the OChem stuff. That's the cool stuff. That's all of OChem 2. Right? But to be able to get to that, we have to understand something about structure all the way through. Kind of, sort of? Okay? And within structure, we talk broad strokes because we have to bring in concepts like resonance. Because resonance is talking about how the electrons move through a molecule. And we talk about chemical reactions. Chemical reactions are how electrons move between two molecules. So I have to know where my electrons are within an individual molecule. That's why we look at structural drawings. That's why we look at hybridization. That's why we look at orbitals. That's why we look at resonance. And all of those things kind of come in because all of those contribute to our overall understanding of what a molecule is and how it can react with something else. So that when you see a drawing, you have to be thinking of all of those pieces. And I know that sounds crazy and nuts right now because you're like, I can barely keep a carbon straight. Okay? But as you navigate through, reflecting backwards, it's like, oh, I can't believe I sucked at that. Okay? And that's universal, I've noticed, with every student that has moved through. It's like, can't we just have stuff about Unit 1? Like, I'm awesome at that now. Like, yeah, I know you're awesome at it because you practiced it for a long time. Good job. But no, we got to move on to this other stuff. Kind of, sort of? Okay? And the better you understand the structural stuff, the reaction stuff becomes easier. Okay? So that's why I'm trying to put a much heavier emphasis with the specs quizzes on the structural stuff as a feedback mechanism. First and foremost, feedback mechanism for you, but also to come back to me, because it initiates questions. Because if I don't have those, guess what class time is? Yep, that was it. That was it. You all are stonewalled, quiet. One person will have attempted the homework, and I will help that one person navigate all the homework. And everybody else is like, what the hell is that structure? Well, if you were following at their pace, you'd be great. Okay? But this way, you're now all forced to be kind of throwing out those questions and to start that conversation. Some of those conversations happen in class. Some of those conversations happen in the tutoring center. They happen via email. If you have not reached out to talk to me, you're doing it wrong. That's the brutal honesty on that. Okay? Kind of, sort of? Okay. We got a question up here. So we got a structure. What do we see? Whoa! Yeah, okay, we see an amine. I would have gone with like an N. Like that would be a good place to start. Okay, I have an N, which means nitrogen, which means amine. What else do I see? I see an O, which means oxygen, which means ether. Okay? But I only know it's an ether because I know that oxygen is connected to carbons, and carbons are C's, and I don't see any C's. All the shorthand stuff, those points are defined as carbons. Okay? So I need to have that information stacked within that knowledge bank so that I can advance forwards. Okay? There's another thing that we should see. Double bond. I should see the double bond. Okay? Okay? And now, the other thing that I should see, lone pairs. When I look at this, the double bond should stand out because it's explicitly drawn. But I also need to be able to see that there are lone pairs within this drawing. Okay? And the specs quizzes are doing effectively advanced OChem stuff, and they're dropping the lone pairs off. For a reason, because they're trying to get you to recognize that you need to be showing them. Okay? So when you draw this out, what you should be seeing is making sure you add all the information that's necessary for you to see all of those implied pieces. So if you want to see carbons, draw carbons. You want to see the hydrogens, draw hydrogens. Depending on the question asked, you can be asked any of those levels. Because I could draw this structure and say, how many hydrogens are there? It was a little mix just to see what people did. Right? That takes a little bit of time to process. But the same structure, I could say, what's a resonance structure? Is that involving the same brain thought? No. I can say, what's the hybridization? How many non-bonding pairs of electrons? How many bonding electrons? What's the molecular orbital diagram? Okay? All of those questions can come from a single structure. So depending on what piece of that structure you're trying to address, you have to shift your focus to each of those branches. Okay? And what's really unfortunate is by the time we move into post-spring break and second semester, all of those branches need to be a continuous stream of thought for you so that you read the question and go, branch gone, branch gone, branch gone, branch gone. I don't care how many hydrogens. I don't care how many lone pairs. I don't care that it's an ether. I care that it's an amine. Okay? So once you've seen now all the paths, eventually you start being able to realize, I don't have to answer that path. Okay? So this structure comes up in an interesting context because what it asks for in the specs quizzes, okay, related to the structure at least, is what's the hybridization? Okay? So it asks for the hybridization for the nitrogen, the carbon, and the oxygen. Right? And for people being like, which carbon? I didn't think that all the way through. We'll call it the red dot carbon. Okay, so I want to know the hybridizations for those. Well, how do we determine hybridization?
Counting the electron groups around.
You count the electron groups around the atom. Okay? Old school, we assume squares. That becomes hard with these structures because old school Lewis structure is all squares, but what we're drawing is three-dimensional models. The three-dimensional models aren't based off of squares anymore. So you have to start to kind of fudge some of that information around. Okay, so if we look at the nitrogen, how many groups of electrons are around the nitrogen? Okay, we'll call it red, blue, green, Come on, pen. And purple. Okay, so that would be 4. 4 groups of electrons would be?
4s3.
That would be sp3. Okay? We look at the carbon. How many groups of electrons?
3.
3 groups. This says groups. Which means?
sp2.
For the oxygen, if you talked, keep your mouth shut. Somebody else.
That's 4 groups of electrons.
Thank you. 4 groups of electrons. Somebody else talk. sp3. And we would go through this process and we'd enter it, and it would spit back that we were wrong. Okay? And the reason why it's spitting back that we're wrong is that in this analysis of hybridization, what we didn't take into consideration is one of the things that can affect hybridization. We're talking about the electron groups. Are all electron groups created equal? No. What do we mean?
Resonance.
Some of them are non-bonding pairs of electrons. Some of them are pi bonds. Some of them are sigma bonds. The sigma bonds can't do anything. They just sit. The pi bonds and the lone pairs have the potential to move. And when we go through and evaluate hybridization, what we're trying to evaluate is not the best structure, but all structures. So what we would go through and do is say, well, what possible resonances can I go through and navigate? Okay? Well, the nitrogen could kick down, could it not? Okay? So we can say, oh yeah, I could totally kick down. Well, let's push to what people have drawn in their homework. So I saw this in the homework. Someone drew something like this. Okay? There's a couple people saying, oh, knock it off. Okay? Because then what that person did, I was like, oh, this is bad. Presumably they said it was bad. This becomes the problem, actually, that I'm going to point out with it. And they drew another arrow, and they said, actually, what I want to look at for resonance would be this. Okay. Sorry. Positive on the nitrogen. Okay, so that's all the Lewis structure stuff. So a couple people were like, oh, why did you say oh? Because it's bad. Why is it bad? We could push formal charge. I accept that. So I'll put the positive charge there. It's still bad.
The nitrogen is not doing what it wants. It's got 4 bonds, but it only wants 3.
Once is irrelevant. It has to do with its ability to move. Does it have the ability to move those electrons? Yes. So I don't care about nitrogen being positive. We could now make an argument which of those two structures is better. The neutral nitrogen is going to be better than the positive nitrogen. Yeah. But I didn't ask that. Okay, I just said what can happen. That's resonance. So why is it bad? Okay. That carbon has exceeded the octet. Okay? And that red arrow, I would argue, shows that that person has acknowledged that we've exceeded the octet, and they have to add another arrow. Okay? But the people grumbling and saying this is bad might have seen that, and they're probably also grumbling because should you draw that? Gray area, no. Okay? That's not a resonance structure, because you've drawn an invalid structure. So that bad thing is bad, and it should never see the light of day. Okay? So when you're drawing that red arrow on top of it, you're now adding extra insult to injury, because you're saying, on this structure that I'm not allowed to draw, I'm going to draw directions for what to do next. You can't draw it, and if it can't be there, does the arrow have any meaning? No. So where does that arrow need to appear? That arrow would need to appear at the beginning. And if we're going to consider resonance, we would be going between those two, and this one would never exist. Do you feel you need to draw that bad structure? right? Which is kind of targeted to whoever drew it and it wasn't this thing, but they did something like this. Okay? Do you feel you need to draw it? If yes, that's okay, but make it darn clear that you're not telling me that's resonance. Put a big old fat X through it. Okay? Say bad. Okay? Bad is still a little vague. Okay? But acknowledge that what you're drawing is incorrect. Does that make sense? Okay. What does this mean? Well, we've now drawn a resonance structure. Well, what does that mean? What was the question that started this whole frickin' thing off? Hybridization. So we've now drawn a resonance structure. Which resonance structure exists? The black one or the red one?
The red one, the arrow directing you towards it.
The arrow is double-headed. It goes both ways, bro. So, black one or red? Okay, and this becomes a nasty question too. Because you get a lot of people saying, well, the black one, because the black one is better than the red one. I didn't ask which one was better. I asked which one exists. Okay, which is already a flawed question. Because not one of them exists. They both exist simultaneously. What we're trying to show by doing these is how the electrons can move. So if I tried to draw me as a person, I could draw, yay, there I am as a person. And I'm a great artist. Like, ta-da, there it is. There's me, stick figure. It's a perfect drawing of me. It's uncanny, the resemblance. Is that still me? Those are different states, but I'm still the same person. I exist at both of those. Resonance exists at both of those. You can't ignore one form over the other because you like it better. Okay? And I know you're like, well, I didn't decide I liked it better. I followed the stupid rules that told me it was best. Okay? It doesn't matter if somebody else gave you the rules to say you like one better than the other. They still both exist. So when we go through address hybridization, you have to exist all states simultaneously. Which brings up a really uncomfortable question. If we look at the black structure, the hybridization is sp3 for the nitrogen. What is it for the nitrogen in the red structure? Well, how many groups of electrons? 3, which means sp2. So depending on which structure I'm looking at, I'm calling it sp3 or sp2. Well, really, the true answer is a blend somewhere in between those. Okay? But what we want to do is acknowledge that resonance is really important, and it's happening. Those electrons are constantly moving. If I say it's sp3, do the electrons get to move? No, because what do I need to do resonance? Lecture on Tuesday. Not necessarily an empty one. I need a p orbital. And if I call it sp3, do I have a p orbital? No, I took all of my orbitals and I got rid of all of the atomic orbitals. I can't do resonance through an sp3. So if I want to acknowledge where the electrons can move, for the nitrogen, I have to acknowledge that resonance structure. And my definition for the nitrogen is not going to be sp3, it's going to be sp2. Okay? Does that suck? Yeah. Okay? But what we're trying to do is be as honest as we can about where the electrons exist within the molecule. They are not localized on the nitrogen. They have the ability to flow from the nitrogen into that carbon.
Can you draw another resonance structure from that structure that's different from that one?
Yes.
So what do you do in this situation?
Okay. So now the kind of next question that he's trying to kind of get at is are there more resonance structures? Yeah. So what do you got to do? You got to draw them all out. You got to be aware of what can potentially happen within those systems. Okay? So let's get rid of that bad one. That was the wrong eraser. Whatever. Okay? Get rid of the bad one and say, what can we do? So the challenge that was put forth is, can I draw another resonance structure from this? Yes, I can. Okay? Where I might try to start would be with the negative oxygen, because that's my highest energy thing. I might try and play with that. And that lone pair on my oxygen really only has one place to go. Where's that one place? Right? And so this becomes a fun one. Someone was like, oh, onto the oxygen. As soon as you say onto the oxygen, that's not one place. That's now two places. If it only has one place, it has to be able to go back from whence it came. Okay? Can it make it to the oxygen? Okay? Number one, atom to bond, I can't drop it straight onto the oxygen. So I have to go from atom to bond. Got all my structures, nitrogen, didn't do anything nitrogen, but there. Yeah. Okay, that's what we're saying. We're moving it towards the oxygen. That's fair. Let's try it. Can oxygen have 3 bonds?
Yeah.
Yeah, it can. Would it be charged? Yeah, it would be positive, right? I just thought positive. Not a big deal, so there it is. What were some of those things that we needed to remember all the way back when we looked at our first drawing?
Yeah, lone pairs.
The oxygen started with 2 lone pairs. Did my arrow show anything happen to those lone pairs? Okay? And for the record, you might be like, but you didn't draw them there. I intentionally didn't draw them there to set up this booby trap. Yay! Okay? This is why we should always draw our lone pairs on. Because if I draw those lone pairs back up here, that now sets me up to be able to see that when I navigate down here, I need those 2 lone pairs also there. How many electrons do I have around my oxygen? Too many. Okay? Which introduces a whole nother cascade of issues. If I have more electrons than I want, what should my charge be? Negative, and yet I've written it as positive. What the flip is going on with this? Okay? What happened is you kind of connected and then just started making assumptions. Oh, 3 bonds, it must be positive. You shouldn't have had 3 bonds to begin with. You made one mistake and then compounded that mistake and compounded and compounded. That's where organic chemistry can become dangerous, which is why we need individual branches of each of those content areas first before we start stacking all the things together. Kind of, sort of? Okay, so we're getting some explosions of questions, which is good. Okay. Do we have any red flags that would help us decide that we screwed up the purple structure before we even address the lone pairs?
Yes.
We have 2 positive.
Oh, son of a fucking horse. Are there other red flags that I didn't screw up? That I intentionally screwed up? Let's go with that. When you do resonance, what happens to the amount of electrons? They just move around, which means your balance of electrons and protons will be the same, which means the overall charge
Should be the same.
is the same. If we look at our starting structure, what was the overall charge? Neutral. If we look at our first resonance, what was the overall charge? Still, and we look at the last one? Ooh, 2 positive. I screwed something up. Okay? So even if you didn't see the lone pairs, hopefully you can recognize the balance of electrons changed and you goofed something. That might be a good opportunity to go back to the red one and say, did I forget to draw something that's important? Lone pairs are very important to draw, and I would argue you should reflex into drawing them. When? All the time. When can you stop drawing them? When you don't make mistakes like this. Which unfortunately really means never. Okay? Why do instructors and teachers and people who write specs quizzes drop the lone pairs? Because they don't screw it up. Okay? In some cases, they're doing it to point out that you're messing it up. Okay? So we'll write questions that target common misconceptions because you will screw it up, and it becomes a problem later on. Okay? So what does that mean? This arrow where we wanted to move it to the oxygen, all sorts of problems, which means and this isn't even a bad, show my work. This is I did invalid stuff. That whole branch is done. Burn it to the ground.
Because the octet is exceeded.
Because the octet is exceeded and there's no way to fix it.
So the octet being exceeded on the negative carbon, how do we find a way to fix that?
How did we find the way to fix that one? So let me backtrack here a little bit and then I have to remember what the structure was. We had that and we said the octet was exceeded. And we just said octet exceeded, burn the branch, and yet up here with this black one, it wasn't burn the branch, it was, oh no, we can keep going. What is different about the black structure versus our purple structure?
There was nowhere else for it to go.
What can move when we talk about resonance? Our pi bonds. I exceeded the octet, I can move a pi bond away from it. I exceeded the octet, I can technically move a pi bond away from this purple one. That's taking the pi bond that I just made and it put it right back where I started. What was the net result? That would be doing this. Purple arrow and now green arrow. Because remember, I can't draw the green arrow on this because this is an invalid structure. What is the net result of taking the electrons from the purple arrow into the bond and then using the green arrow to take the electrons right back? The exact same thing. There is no difference. That's why I would argue it's a burn the branch. Okay? Because you didn't take it to any place that you could navigate away from. You took it to a place that was a full dead stop, dead end. Okay? So where else could I move those electrons?
Back where they came from?
Back from whence they came. Okay? So I could move those electrons back, which would then do what? Exceed the octet, which would take me to a nasty structure I'm not allowed to draw. So what do?
Draw a green arrow to the nitrogen.
Take a green arrow from that pi bond up to the nitrogen. Okay? If we remember the challenge that Andrew dropped, what was the challenge? Can I draw resonance structures or arrows on this red structure to take me someplace new? Did I just go someplace new? Nope, I went right back to the beginning. So does that mean I lost? No, I didn't finish. Okay. Did I screw that up? Oh, no, I didn't screw that up. Okay. Sort of. What I'm seeing in my head isn't correlating with those arrows.
Need the pi bond still.
Didn't move one of those lone pairs. But the nitrogen, why am I drawing the nitrogen up there? Nitrogen there, there. And we'd have that, right? Do you agree with me? Is that what the arrows show? I don't care about right or wrong. Is that what the arrows show?
Yes.
Yes. Okay? This becomes really, really critical. When we deal with resonance, we're talking about how electrons move. Guess what? After spring break, the rest of the semester and all of OChem 2 is all about. How electrons move. So if you understand it now, you've got a wicked jump start on everything afterwards. If you're even shaky now, you've got a wicked good start on everything afterwards. Okay? So what we're doing is following the instructions that were written. Are these instructions going to work for us? What's the problem with this drawing? Where does it exceed the octet?
The carbon that has full 7 pi bonds.
Why? I only see 8 electrons around it. Isn't that good?
Implied
How do I know I have an implied hydrogen? That was awesome.
Because when you look at the original structure, you see a double bond, a single bond. Yes. And
We
it's
knew there was a hydrogen back there. Why is it important to know about your hydrogens? Because today it helps to point out. So I have to be aware of those systems to be able to track what's wrong or right. So this means what I have drawn is incorrect. So does that mean Andrew wins?
Yeah.
Not quite. I really want to be able to draw it from the red one. I don't want you to win.
You can't just go back. Just take the purple and put it on the carbon right there. And say bad. Circle it. Say bad, and then point an arrow.
You know what? No. For the way I've described the rules,
I can't.
you win.
So for the.
God damn it. Is there another resonance? Yes. I just can't get there from here.
For the test, we're supposed to like do all this trial and error.
Which brings up another fun question. Should you be doing all of this trial and error for the test? No, because theoretically what would happen? You've already encountered that if you move the electrons in that place, you know it's going to be a dead end, so you don't do it. This is why it is so critically important for you to fail up and down right now. You need to be able to find what it looks like to be a dead end. You need to be able to look at it and be like, dang, I don't have the rules to get to another resonance structure. For the record, was that easy to do? No, I screwed it up. I thought I could do it, and I'm a little irritated I can't. Okay? I can still get another resonance structure, though. I just can't get there cleanly from the red structure. Okay? So, why do I know I can get another resonance structure? Call attention to it right here. I know the oxygen has the potential to move those electrons. I'm just doing it from the wrong drawing. I need to go back to my starting drawing and say, how could I do it? If I move them there, now what happens? Exceeds the octet just like we drew, except that exceeded octet has another pi bond that I could move. Those extra arrows whoop, not another lone pair there. Since I keep missing the charges, I'll try and do better. Take me there. Okay. And Danny, you asked an awesome question. Are you expected to do all this trial and error? What's the charge on this oxygen?
Positive.
Well, oxygen has 6 valence electrons minus the 3 bonds minus 2 non-bonding charge equals a +1, so I should be a +1. Are you expected to write out all that work on the exam? No. What you were expected to have done is enough practice that you see that fast without having to run the calculation. Exact same principle applies with resonance. Have you done enough practice to see how the electrons can move? So now I get 3 resonance structures. And I don't have a good way to go back and forth between the red and the purple ones. I just don't. Okay, but I can get to the black one from either the purple or the red. Which of those structures, let me get rid of the black one up there. That one's bad. Which of those 3 resonance structures exists? All 3. Which means when I'm asked the question about hybridization, I have to consider all 3 in my answer. So when I look at the nitrogen, I'm considering all 3. There it had 4 groups. Here it has 3. Here it has 4. That scenario where it has 3 becomes critical because it shows that it can do resonance. That becomes my answer for my hybridization, which means the nitrogen must be called sp2. The carbon, we go through. Here it's sp3 in the purple, right? And the red, it's sp2. And the black, sp2. What's critical for the resonance? sp2. Carbon's sp2. What's the oxygen? sp3 in the black, sp3 in the red, sp2 in the purple. What's critical to show that I understand resonance? sp2. So the hybridization comes in as sp2. So all 3 of them should be labeled as sp2.
So we don't say that they could be either. We say them like lowest possible.
Okay? And you use the exact same wording he did, which has never crossed my mind before. Okay? So in this, if you're given a choice, which one do you say, SP3 or SP2? Well, we just said SP2. Why should we say the SP2 over the SP3? And there's a couple things that come out of it. This lowest is an awesome way to describe it. Why is SP2 lower than SP3? It's lower in energy. How do I know it's lower in energy? What was that?
Less electrons.
We haven't actually specified electrons. We're just saying that's the hybridization. In fact, the number of electrons around it are the same. Flip it, different question. We'll come back to the lowest energy. How many orbitals did I need to make sp3?
1s and 3p.
1s and 3p, so do the math. Answer my question. 4. How many did I need to make the sp2? 3. And 3 is smaller than 4. I needed less. Okay, what's the difference between s and p? A little bit of shape and size. The p are slightly larger. And since the p are slightly larger, they are higher in energy. And if they're higher in energy, if I have less p's, sp2, I am, again, lower in energy. Whoa, that lower was just amazing. Kinda? Ballet. First. Make sense?
Which diagram is oxygen sp2?
You tell me. Look at the black. How many groups of electrons are there?
4.
4. So it would be
sp3.
lovely. Look at the red.
There's 4.
Which means?
sp3.
Okay. Which means? Not that. Okay.
There's 4 groups still. Right? 1, 2. Stop. Okay, thank you.
Okay. Which is a common mistake. We see the double bond and we try to draw that as a second group or a third group if it's a triple bond. That is one group of electrons. There's 4 electrons there, but that's still in one space. Okay? Depending on how you draw, and I would argue where you're making that mistake is that I drew my oxygen slightly shifted low. So it looks like that is an extra line kind of coming in from the top, which is probably what you're doing. Which is why really important to draw nice. Right? So how you draw your structures can change your interpretation. One of the reasons why you have to learn how to draw them. Kind of, sort of? I think that's it. Other questions about what's up there? Is that a vigorous no, like please stop?
No.
You've killed it.
I just don't have any questions.
Okay, that's good. I appreciate that.
So in one of the exit tickets, this was like an exact question. So
Sort of.
yeah, but it was
Close
like
enough.
SP3 and SP2. So we were supposed to like rewrite another structure similar to it. So we find two. Of
So,
what it could be.
because what the question was what was the hybridization for the nitrogen, carbon, and oxygen?
Mhm.
Well, if you look only at the black structure, you would get these black answers. You would only get a third of the points. To get all the points, you have to acknowledge the nitrogen and oxygen are sp2. How do you know they're sp2? Because of all the other structures. So when you're looking at a question that's asking about hybridization, do you think it might be important to also draw resonance? Which quiz came first, by the way, resonance or hybridization? Good. Okay. Resonance sets us up to be able to answer the hybridization correctly. If you're like, but it takes a lot of time to draw it in the computer, you're not drawing it in the computer. You're drawing it by hand. Draw it by hand as swiftly as possible. The faster you pick up that speed and fluidity with doing that, the faster you can interpret your question. Does that help?
Mhm.
At the same time, it's kind of depressing. Okay. What things could we look for to help us recognize that we've got resonance? Lone pairs. Lone pairs is a giant red flag. We should be looking for resonance. But if I draw I don't know. We're just going to stick with that. Do I need to be worried about resonance?
No.
Why not? It's got lone pairs.
Um,
I didn't want to do that.
everything seems equal with the implied hydrogens, and so it doesn't seem like it could move anything.
So everything seems equal with implied hydrogens. So you're saying the black structure that we initially started with seemed unequal?
Yeah.
Why is looking at that one make you go, oh, I can do resonance, but the purple one you can't?
I would say the pi bonds in the middle, that's kind of a red flag for me, like, oh, fucking, a pi bonds in the middle with,
Is the pi bond in the middle now?
yeah.
Yeah, fuck you, Mike. Why'd you do that? Your answer sucks. Try again. You are so right on the right wavelength, though. What we're trying to describe is the common patterns that we see that allow us to know whether resonance should happen or not. Yes, that's very, very valuable. But middle is pretty freaking random, as we can see with the purple one. Yeah. So why is the black one, again, resonance, but the purple one not?
Symmetrical.
I can draw that structure and make it symmetric, and it's still going to screw up your answer. So no, but don't make me draw it again.
Because you're close.
You mean the distance between the lone pair and the pi bond could have an effect? Yes. That's really important. If we go through and look at the black structure, lone pair, sigma bond, pi bond. Look for the oxygen. Lone pair, sigma bond, pi bond. Look for the purple structure. Lone pair, sigma bond, pi bond. Ooh, so the presence of that extra sigma bond blocks the ability to do resonance. Okay, neat. Perfectly legit observation, but of course we got to make it more difficult and say why. And as a perhaps not so subtle hint, what do you think LP stands for? Okay, lone pair. If you didn't know that was an L, that's an L. What's happening in the purple structure? So did the black structure. So I don't accept just that it has lone pairs. Because it has lone pairs, it has the potential for resonance. So it could be sp3 or sp2, right? Technically, it could also make it all the way to sp, but that's edge case. Okay, so that one's hard to nail down. So let's leave that one alone. If I want to get to that pi bond, I have to move through a carbon. Then I can get to the carbon of my pi bond. What are the hybridizations of the carbon of my pi bond? Blah. Of the pi bond, these two. sp2, implied hydrogen, those are sp2. What's the hybridization of that guy? sp3. What does the nitrogen have left over if it's an sp2 in the black?
Pi orbitals.
Try again.
One pi orbital.
Try again. A p orbital, thank you. What does the carbon have left over? P orbital. What's the other carbon have left over? P orbital. What does the oxygen have left over? P orbital. Because I have p orbitals, guess what the electrons can do? Hop to hop to hop. Move over to the other one. Let's just, for giggles, say the nitrogen was sp2. Let's just say, I'm going to make it do resonance. Okay, we can't. But let's just say it was. Or here, let's fix it. Now it's sp2. Okay. what would it have left over? P orbital. What do the sp2 carbons have left over? P orbitals and p orbitals. What does the sp3 carbon have left over? Nothing. So when we're talking about our hybridization, we have an atom, and our atoms have an s orbital, and they have 3 p orbitals. And so when we're talking about hybridization, if I'm saying sp2, what I'm saying is I'm taking the s and those 2 p orbitals, and I trash them, and I turn them into sp2. Okay? What was not hybridized? What's left over? That's that p orbital. If I have sp3, what does that mean? I'm taking all 4 of those, and I get rid of them all to make sp3. What's left over? Nothing. Why is that important? When we talk about resonance, what do we need to do resonance? We need overlapping p orbitals. And if I have an sp3 atom sitting in the way, there is no p orbital to overlap with, which means you can't do resonance through that atom. It blocks the system. So that observation of where the lone pair was relative to the pi bond was critical, because what that's setting up is p to p to p to p, which is a little foreshadowing, unfortunately, because I had too much water. TMI. Kind of makes sense? Hopefully about the chemistry part. Okay. So is the distance important? Yeah. So it's not that it's in the middle, it's where it's at with respect to the other electrons that can move. Should we try another one? Lots of head shaking no, which means of course we should do another one. Do I have any lone pairs?
I just looked up.
Do I have any lone pairs?
No.
No. So this means I have no resonance.
No.
Good, no. Because what can also resonate? Pi bonds. Do I have pi bonds? Yeah, I have a lot. How many pi bonds can do resonance? So to help with this, we have 1, 2, 3, 4, 5, and 6 pi bonds. How many pi bonds can do resonance?
All of them together.
So all of them can do resonance together? No. Some people said 5. Did you draw all the resonance options?
No.
Why are you saying 5?
Because you highlighted one of them. So.
Ah, interesting. So I drew one a little bit off. But why didn't you say 1?
Because all the other ones have implied hydrogen bonds.
Yeah.
There's implied hydrogens on that green carbon too. What's that one carbon? sp3. That one carbon turns off the ability for the green to talk to the red. Why can the reds all talk to each other? Pi, sigma, pi, sigma, pi, sigma. You mean that repeating pattern that you pointed out so lovely over here? Yeah, they all match. All those pi bonds can talk to each other, except for the green one, who's now been isolated because of that one sp3 atom in between. All right? We could push on, what's the hybridization of our first carbon? The black arrow. sp2, what's left over? 1p. What's the next one? sp2, what's left over? What's left over? This is not helping. Okay, now we're stopping with that. Okay. We good?
Would it be better to remember it as like 2 sigmas or like the actual repetition like it's
So deciding what is better to remember this process as is a interesting question, and it's not a question I'm sure you want to be happy. You would be happy with my answer, because it is not better to memorize anything. What is it better to do? understand how the electrons move and flow. Okay? A lot of that understanding can fall back on, okay, what I would call a cheat, which is absolutely fair. Memorize a current pattern that you know works. Okay, I get it. Okay, you're limited time, you can't understand everything. Okay, so you're going to have to memorize something. Is this where you want to memorize? I don't know. I can't answer that. That's going to come down to you deciding where I want to start memorizing. Okay? Because if you've talked to people in OChem, okay, that took OChem in the past, you've probably heard them complain about it, if they were one of the people complaining about it. Oh, it was too much memorization. And then you ask those same people how they felt about anatomy and phys, and they're like, oh yeah, it was easy. What the fuck is anatomy and phys? All you do is goddamn memorize everything. There's nothing else to it, it's just memorization. What is OChem? It's not memorization, it's application, and that's where you got screwed. Because you could memorize the bejesus out of everything, but you had no idea how to apply it to a new structure. And as soon as I throw up a weird, goofy structure with 1,000,000 double bonds, you immediately go, oh my God, that's impossible. No, it wasn't. Take that deep breath, slow down, pull back, and be like, oh, yeah, there's that pattern. I get it. Okay? But OChem will constantly change structures on you. And if you're looking at it as a structure for an answer, you run into a problem. What you have to be looking for are the patterns within those structures. That's an application. Yes, that is hard. That takes time, right? And full disclosure, I failed the first time I took OChem, miserably. Okay? It was, technically I didn't get an F, because I was failing enough that I knew I should leave. And so I took a W and came back and retook the class. And I changed how I approached the class. When I first took it, I went through it the exact same way I did Gen Chem. I just crammed for the test, spit it on the test, and I'm done. Okay? And I did awful at that because there was too much to just cram and memorize. So when I went back a second time, I changed my approach and said, I'm not doing that. What stuff do I think is useful? Okay? How could I potentially apply this to different scenarios? And I started looking for patterns. Okay? Slow build up. Right? But by the end of the semester, or technically quarter, I could now process where things were moving much faster than my colleagues that had memorized things, because when the structure changed, I was in lockstep. Right? But that meant I had to accept losses. One of those losses you were already very aware of, nomenclature. Said, nope, not doing it. Shows up on the exam, I go, that's one carbon, let's call that a methyl. What's the rest of it? I don't know. Move on. I'm not going to waste my time on something that I can't use in multiple locations. Right? So I've changed how I present the class and base it kind of around that experience. Because nomenclature made up 10% of my grade when I took OChem. I got an 89 in the class. That's a B. Okay, I accept. That's a B. I straight up did not do 10% of the class. I absolutely 100% deserve a B, because I chose not to do it. Right? I want you to do better, and so what you need to do is decide where your line is. Okay? Anything that involved memorization, I just kind of went, nope, not doing, not worrying about it. I'll figure out how to apply it. Okay, there's questions that just predict the product. I would draw a frickin' mechanism on how to get there. It would take me twice as long, but I would get there, and there's the answer. I'd be like, yeah, I got it. I only got 20 more of those in 5 minutes. Right? So yeah, scores would tank a little bit because of that. Okay? I accepted that and owned that. You've got to decide where you're going to be. Are you going to try and memorize everything? It's not going to work well. Are you going to try and apply everything? Also not going to work well. Because you don't have time to apply everything. You have to find the blend of what you're memorizing and what you're applying as you navigate the system. And what you'll find early on is there's a lot of memorization that slowly becomes able to transition to application. And you can start forgetting that because it's already become innate within your structure. You look at it and you know how many hydrogens, not that good, but you know how to count how many hydrogens there are. Okay? You would know the process behind how to get there without having to stress about being super detailed. Kind of make sense?
You're going on this whole spiel about memorization, but I swear to God, the forces and knowing the slight, minute difference differences in boiling points.
It's not very fun.
True. How much experience have you had with that?
Probably 5 minutes in one of your lectures.
Okay, so cool. After 5 minutes, you are not an expert. I'm
Yeah,
sorry to
that's
tell
why
you. Yes, you are not an expert. Okay, so let's spin something out. Minute differences. What is its boiling point?
Pretty high. A little bit higher.
Everyone's like, what the hell? How am I? You're not supposed to know that. Were you ever asked to know that? No, so don't worry about it. What's its boiling point?
Higher than that one.
Whoa, we just got a couple different answers. You're going to go, oh, it's 100. Okay, cool. That's fine. Were you asked to know that? No, you've memorized it. Okay, was that useless information? Yeah, 100%. That was absolutely, utterly useless. You shouldn't have done that. Okay, I get it, but I mean, I've got it memorized too. But what's the question? It isn't which one of these has this boiling point. But what I will go through and do is now say relative to each other, which one should have the higher boiling point. I can even give you a list of numbers. And you could point to two numbers that relatively differentiate them. That's all we care about. Okay? And the quiz may be different. I got to look at that a little bit deeper. Okay? So we'll poke at it, but I would bet it's doing the same thing. So why is this one, our water, higher than it is for the top one? What dictates boiling point? The forces. Okay? So what force would you expect out of this top molecule?
Hydrogen bonding.
Hydrogen bonding. Cool. What do you expect out of the bottom one? Hydrogen bonding. So you just told me that the bottom one should have a higher boiling point because it has a stronger force, and you're telling me they have the exact same force. So you mean there was more to the picture that you were evaluating that you didn't bring into this. This top one also has London dispersion forces. Okay. Well, it has more forces. Shouldn't it be higher? Why not? Okay. And we can talk about the costing energy to make. You don't even need to bring that in. Top one has more forces. Technically it doesn't, but it has more forces. Why is the top one not a higher melting point or boiling point? Okay, it's not just what are the forces, but now what are their strengths? Hydrogen bonding is a strong attractive force. Okay, London dispersion is a weak attractive force. So if we look at this top one, we're getting a strong force and a not strong force. Whereas water on the bottom is strong force. Which one's going to be stronger? The one that just says stronger. Ta-da! It should have the higher boiling point. And the other one should be lower. Okay? That's it. Forgot to draw lone pairs. Just realized that.
A dipole. Carbon, oxygen.
Okay? So I didn't even say anything, and you're immediately starting to go through, okay, well, I need to look at the force. So you're saying this one, you just said was dipole. Is dipole a force?
Dipole.
Thank you. Okay.
And there's two, I would say, one on the left, there's a London dispersion force, and the other London force, whatever.
Which one would we expect to have the higher boiling point? Why? Hydrogen bonding versus dipole-dipole. Hydrogen bonding is a stronger force. I would predict the top one to have the higher boiling point. Okay. That's it. Yeah?
I mean, yeah, but on the specs quiz, it has I really don't care.